Okay, good morning. This is APL, and if you haven't already done so, if you go to the conference page about this workshop, you can download Dialog, which is a version of APL to which they added a lot of extra stuff. So we're actually going to work in APL. Let me share my screen if I figure out how to do that. There we go. Okay, I am screen sharing. Great. So first thing I'm going to do is, oh yeah, I don't need that anymore. In Snap, I'm going to load the APL library. So file menu. You don't have to do this because we're actually going to be working in APL, but I just wanted to show what it's like. And down most of the way to the bottom in the third chunk of libraries, we have APL primitives. And what the APL primitives are, they have a bunch more arithmetic functions. So factorial is a primitive, combinations are at a time of n, log to any base, minimum, maximum, plus with one input, monadic plus as the identity function. This one is not an exact mapping of an APL function. It's some of the snap primitives we didn't make hyperblocks out of because they mean something when applied to lists. And those are the equality testers, equals, and here's not equals, and identical to. And also the lazy logic functions and or, and is blank a blank. Obviously, if you give that a list, it's going to say list instead of whatever the pieces are. But we can, well, why don't I actually do that? Let's see what happens. So I'm going to make a list whose items are 87, hello, whoops, and list. And I'm going to make this be the is blank a blank function. So let's find the things that are numbers here. And we get true, false, true, true. Well, that's interesting. If it goes all the way down, I wonder what we'll get for a list. Maybe nothing at all. Yeah, it's all false. Interesting. I'm not sure if that's the right behavior or not, but it's certainly the APL behavior. It's the work all the way down to atomic values. So that's just to show that off. And then I wanted to look at the APL functions that are not scalar functions, but inherently take lists as inputs. So here's Reshape that takes a bunch of values and makes an array of certain dimensions. So if I say 2, 3, put some numbers in there, I get 2 rows, 3 columns. And it stops at 6. That's all the values it needs, even though I gave it 10 numbers. And conversely, if it were 20 by 3, it would cycle through the values repeatedly. So that's an interesting APLism. But mainly the point here just is that almost all of the APL primitives are represented here, and they're represented including in yellow the APL symbol for whatever the operation is. So Reshape is the Greek letter rho, and so on. Okay. So part of learning APL is learning all the funky symbols for things. And they use the symbols partly to avoid having any reserved words in the language. So most programming languages, there are things like arithmetic operators that, plus, minus, times, divide, symbols in between 2 values. But then there's functions that are named, like sine of 23, right? Here, if you want the sine of something, or any trig function, there's this circle operator. Circle operator takes a left input and a right input. And the left input is a small integer, a small magnitude integer, saying which function we're talking about. And the right input is the value that we're trying to apply the function to. So sine of some angle would be 1 circle the angle. So that's sort of taking to an extreme, trying to not have reserved words by using symbols for everything. The other reason, though, is to try to look like what mathematicians write on the chalkboard, except for exceptions. And there are some exceptions. The one that drives beginners crazy is that operations are always grouped from right to left. There's no multiplication before addition. So if I say 5 times up here, two plus 3, this doesn't mean 10 plus 3, it means 5 times 5. Okay? So that only drives you crazy for the first day, then you get used to it. and they do it for two reasons. One is that there are just too many operations, all these things up here, to try to establish precedence rules for them all. And the other is that in APL, it's very natural that often grouping right to left is what you want, and you don't have to use parentheses for grouping. If you forget about plus and times for a minute and think about all these other operations that aren't so familiar, they usually do build expressions up right to left. Sometimes you need parentheses for a left input to something. By the way, let me introduce the words monadic and dyadic. A monadic function is a function of one input. A dyadic function is a function of two inputs, and the name of the function goes in between the two inputs. In the computing literature, these are often called unary and binary, but those words have other meanings in computer science. So when you talk about a binary function, everybody gets confused. Do you mean binary numbers, or do you mean two inputs? So APL introduced the names monadic and dyadic for that. And all APL functions are monadic and dyadic. There's no functions of three inputs. You can do it, but it's not a very natural thing to do in the language. And this turns out hardly to be a restriction at all. It is a little bit, but usually you get around it by putting all your inputs in one list. So I thought I would begin by showing you the APL computation that turned me into an APL lover when I was 14, which is too long ago. So this is a graph of a function. But it's also an array of characters. And it's produced as an array of characters by this code. Can I remember what del is? Yeah. Okay, so this long string of gibberish produces that graph. And don't panic. I don't expect you to write things like this or even really read them first time around. I'm just trying to show you what the endpoint is so that I don't get rushed at the end. So the way this works is we are going to make a matrix of characters, an array 21 by 21. And I picked that funny value because the axes are plus 10, minus 10 to plus 10, which including 0 makes 21 positions. So the key point to see here is this. This is an array of characters. It's a text string. And it has the complete set of characters that are used in the graph, starting with space, which most of them are. And then the next three are to draw the axes. Minus where y equals 0, vertical bar where x equals 0, plus where both of those are 0. And then finally asterisk, which is what I use for the actual function plot. So how this works is that we're going to index into this text string. Well, how is the index computed? And we use repeatedly this sort of upside down L character, which means ceiling or a maximum. So we're going to take the maximum of 5 different expressions. What are the expressions? Well, the first one is just 1, and that's because, like Snap, APL does one origin indexing of arrays. Next one is 2 times a bunch of stuff, and the key point about the bunch of stuff is what's in braces here. This is a function, sort of defined on the fly function, like a gray ring. Since functions are at most dyadic, APL provides the symbols alpha for the left input and omega for the right input. So those are the endpoints of the Greek alphabet. So here we're computing alpha equals 0. Took me a while to realize why alpha and omega are what they are. Alpha turns out to be the y value, and omega turns out to be the x value. And where these come from, let me get out of this function here. Where these come from is x and y, which I have previously set up. That's x. That's y. Well, y makes sense. It's the number line. What's going on with x? Why is it backwards? And the reason it's backwards is that in an array, the topmost row is row 1. The next row is 2, and then the maximum numbered row is at the bottom. That's the opposite of what we want for y values. So you'd think it would be y values backwards. But no, I'm sorry, it's the opposite of what we want. Right, I'm confused again. The way I actually came up with this x and y is by trial and error. But let's, for a moment, hold the question of the ordering of x and y and look at this. That little circle, the big circle that we used for trig functions is called circle. This little circle is called jot. So this is jot dot and then a function. And that represents inner product. I'm sorry, outer product. Too early in the morning. What's outer product? Well, let's do this. About the funky symbols and how you type them. You can type one by just finding it up here and clicking on it. But also, it shows you a keyboard alternative, a sort of multi-character sequence. This is a back quote, the character which, at least on American keyboards, is in the top left corner. Not to be confused with backslash. This is back quote. So I'm going to come back down here and say iota 5. And that's numbers from 1 to 5. Okay. So now I'm going to say iota 5 jot dot times iota 5. Note in passing that I parenthesize the iota 5 in the front, not the one in the back. Why? Because we do grouping from right to left. So 5, okay, iota of that. And then jot dot times is a function. So that's essentially a single symbol. And then if I didn't have the parentheses, the left input to jot dot times would be 5. And I would get whatever array that produced, and then I would try to take iota of that. So this is a case where we need parentheses. And what we get is the multiplication table. Because we take all of these numbers multiplied by all of these numbers. Might be interesting. See that? Aha, yes, and now I can understand the order of inputs. So iota 5 is what determines the rows. Iota 6 is what determines the columns. Right. In the graph that we're making, if I do X and Y, X is determining the rows, and Y is determining the columns. And it's the rows that are backwards from the order that we want. So we would like 1 at the bottom, 5 at the top for making a graph. Whereas the columns are in the correct order. So that's why one of those had to be reversed. Okay, so back to my function. I took this expression, x jot dot alpha equals 0 function of y, and I multiplied it by 2. Maximum 3 times the same x jot dot something y, but this time it's omega equals 0 to get the vertical axis. And why am I doing 2 times 3 times? Well, we want the maximum, we're going to get the maximum of these 2 values. Most of the time, most of the values will be 0, will be 1, sorry. No, will be 0, right. And so the whole thing will be 0, meaning false. 0 is false. So if these conditions are false, then it doesn't matter what we multiply by because we're multiplying by 0, right? Whereas if they're true, and let's say that more than one of these is true. So at the point 0, 0, alpha equals 0 is true, omega equals 0 is true, alpha equals 0 and omega equals 0 is true. Which one of these is going to determine the character that we print? Well, whichever one is multiplied by the bigger thing. So it's going to be 2 times 1, 3 times 1, 4 times 1, and the maximum of those is 4 times 1. And so we get the character number 4, which is the plus sign out of this string of characters here. Character 1 is the space, always good. Character 2 is minus, that's y equals 0. Character 3 is vertical bar, that's x equals 0. Character 4 is plus, that's x and y are both 0. And then character 5 says y equals ceiling of x, and then this upside down t thing, and then a list of coefficients. So what's that about? Let's go ahead and show you that operation. 5, there's no way I'm going to remember this. It's backquote B, of course. 1, 0, 7. The answer to that is 32, which is 7 times 1 plus 0 times 5 plus 1 times 5 squared. So 25 plus 7 is 32. If I do 0 times all that, I just get the constant term. Okay, so this is a polynomial. This is the value that we're applying the polynomial function to. And there's a single APL operator to compute that. So back in my graph, I am graphing 1/3 x squared minus 3 1/3 x plus 1. And that turns out to be this parabola. Well, that's pretty terse. And it's worse for you guys because you're seeing APL notation for the first time. So let's do some other things. Let's see. I'm going to make a matrix. Matrix gets 3, 4, reshape. You can start playing along. This is a good time to start playing along. 3, 4, reshape, Iota, 12. And so M is this matrix. So how about M plus 5? And what we see is, just as in Snap version 6, the 5 is added to each item of the matrix, and the result that we get is the same shape as this first input, and having added 5 to each value. Well, how about m plus m. That does the obvious thing. It term-wise adds 1 plus 1, 2 plus 2, 3 plus 3, 4 plus 4, 5 plus 5, and so on. Oh, my voice is going. Okay. Well, what if I do m plus, and then I give it a vector, a one-dimensional thing, 1, 2, 3, 4. I get an error. This is different from snap. Snap is going to extend this vector and use 1, 2, 3, 4 repeatedly. I guess I could show you that. So if I reshape as 3 or items of Iota 12, I get that same matrix that I had before. And now if I, if I add to that matrix well, I have one here. So instead of using Iota, I'll use the snap version. Thank you. So this actually does something. It adds 1 plus 1, 2 plus 2, 3 plus 3, 4 plus 4, and then 5 plus 1, 6 plus 2, 7 plus 3, 8 plus 4, 9 plus 1, 10 plus 2, etc. So snap actually is more permissive in terms of shape mismatch than actual APL is. In APL, by the way, just so you don't get messed up about this, asterisk is not used for multiplication. So I guess we use yeah, asterisk is used for power, and multiplication is the X symbol. So that's APL speaking mathematician and not making any concessions to speaking computer scientist. By the way, if you're teaching CS principles and the College Board wants to know what is some string of digits in binary, 2 upside down tack, 0, 0, 1, 0, it's 18. That's 16, 8, 4, 2. So 16 plus 2. Or alternatively, we can do right side up T. It's called down tack. 18. Oops, maybe we can't. do I mean 19 down tack 2? Nope. What do I mean? Ah, yes. It has to be a whole vector full of 2s. I was right. This is all wrong, but this is almost right. If I do for reshape 2, I guess I had better put that in parentheses. Down tack 18. Oops, I only got 4 digits. So let's make that 5. And now I get the correct decoding, the correct encoding as binary of the number 18. And by the way, I keep telling people not to say translate decimal to binary or binary to decimal, because you're really converting binary to number and number to binary. And a good way to make that point is to convert the number 18 into the decimal numeral 00018. Okay, so a numeral is a string of digits, whereas a number doesn't have a representation. We represent them in decimal for the sake of typing them in and out. But this is really the number 18 and not the digit string 18, whereas this is the digit string 18. Okay. This is kind of the blind leading the blind, because I haven't really programmed in APL since I was 14. But let's do this. Dot greater than Iota 5. So this is a graph of a greater than relationship. And you can see you get a 1 where the value of the row is greater than the value of the column. We can also do inner product like this. If instead of this jot, I put a plus sign. That is not what I expected to have happen at all, actually. I expected to see, oh, well, okay, wait. Very interesting. See, if I make this plus dot times, oh, duh, I'm an idiot. Sorry. I still have my matrix? Yes, I do. So let's do matrix plus dot greater than matrix. And we get a length error. Correct, because I'm trying to do matrix multiplication. And to do that, the number of rows of the guy on the left and the number of columns of the guy on the right have to agree. So let's do plus dot greater than transpose M. There we are. So just to be clear what the transpose of M is, it's this. So this 0 represents 1, 2, 3, 4 greater than 1, 2, 3, 4 term-wise, and then add those up, and we get none of them is greater than. If I did greater than or equal to plus dot greater than or equal to transpose of M. Now, the first column of the result is all 4s. Why are we getting these 4s? Well, because we're adding up these Boolean values. So this is a thing that APL does. It very dramatically takes advantage of the fact that Boolean values are also integer values. So you saw before how we can use Boolean values to index into an array. So this is plus dot times would give us the traditional matrix multiplication. But we can do matrix multiplication with any operators we want. So instead of, for example, instead of plus dot greater than or equal to, I could take and dot greater than or equal to. Or I could take or dot greater than or equal to. In this case, I get the same answer. Because the way the ordering in the matrices work, either they're all greater than or none of them are, because they are in ascending order in both matrices. So this one is, which is the sort of most interesting one. If you remember how matrix multiplication works, each cell of the answer combines a row of the left matrix and a column of the right matrix. And the way you do the combining is you multiply the numbers term by term, and you add up the results. And that gives you one cell of the result. So we can generalize matrix multiplication to use any operations we want. So here we have and dot greater than or equal to, which is, it's not the standard matrix multiplication, but the algorithm is the same. We take a row of the left matrix, a column of the right matrix. We use greater than or equal to term by term, and then and the results together. Is it all true? Oh, I did want to show off these 3 circles with lines through them. The lines are an axis of symmetry. So the vertical thing says, flip the matrix around the vertical axis. So you reorder the columns and keep the rows the way they were. Horizontal line, it's the other way around. It flips, it reorders the rows. Well, you can see the example here. So the columns are in the same order, but the rows are flipped around. So the horizontal line is the axis of symmetry. And a transposition, the axis of symmetry is diagonal, right? You flip. So what used to be rows is now columns. What used to be columns is now rows. And you can do this, as you can see in this example, not just to matrices, but to 3-dimensional arrays. So this is 1, 5, 9, and then 13, 17, 21, taking this vertical slice through 2 planes and making a matrix out of it, and so on. So in real APL, I didn't want to do that. In real APL, I should say, they're very fussy about the shapes of arrays. Arrays have to be sort of full, every dimension filled up. Whereas because we represent a matrix as a list of lists, each of those sublists could be a different length. And also our data are heterogeneous. Each item can be, one thing can be a number, and another thing can be a list, and another thing can be a procedure. But in APL, the original APL, either every item is a number or every item is a character. Those are the only choices you get. They don't have character strings, except in the sense that you can have a vector of characters. And that when you print a vector of characters, they're right next to each other. You don't put spaces in between. I'm trying to decide if I should now just stop talking and let you play. Should I do that? I think so. I think you should play with this. Oh, I'm sorry. I was going to say later versions of APL, there's an APL 2 in which they added snap style heterogeneous arrays in a very complicated way. So why don't you go down these rows of symbols and familiarize yourself with the operations up to transpose, and then stop, because these other things are special APL 2 operations that who aren't interested in it. So, so learn the operators and look at their examples and figure out how you would write programs by combining things. Do that for a few minutes while I look up some good examples to try. From my textbooks here. Oh, look at that. Time flies when you're having fun. Okay, so I should just wrap up by telling you a couple of little things, which is they didn't have keyboards with a million symbols. Instead, some of these are made by backspacing and overprinting. As APL was invented back before display terminals were invented, you used like typewriter terminals. So this is slash backspace minus sign. This is circle backspace vertical bar, and so on. And higher order functions. So instead of map, we have hyperblocks. That, you saw Jens demonstrate that. Instead of keep, this is a Boolean vector, and this is the operation reduce or select. We select yes, no, yes, yes, no from this vector. Yes, 1, no, 2, yes, 3, yes, 4, no, 5. And we get 1, 3, 4. So this is like our keep, except that you would put the Boolean computation, you would make a vector of trues and falses, and then use that to select the items from the original list. And reduction is done like this. You take an operator like plus, slash, 4, 5, 6, 7, and you get 22. So that adds these up. And we're out of time. Thank you for coming. I hope you're intrigued by APL, in which case, go find a book in the library. They're really expensive, even used these days on Amazon. Yes, Jens is showing his APL book, APL 2 at a glance. There are lots of them. They have strengths and weaknesses. Dialogue, the people who make this particular version of APL, have a tutorial for it, which is this thick. It's almost 800 pages. And it costs an arm and a leg, but it's really kind of worth it. Okay, thank you.